In a previous video, I made a neural network regression code for this very simple data set and showed that if I run 15,000 epochs, I get a very low L2 loss, right? But I do see some signs here of overfitting, so you can see that here. You can also see the fact that for my validation set, I mean for the points not used in the fitting, right, the error is larger than some of the blue points here, which I did use for the training. And so that's an indication of overfitting. So today, in this video, I want to demonstrate one way to deal with it, and that is called early stopping. So that is basically monitoring the L2 loss for the validation set instead of the training set. So I need to keep track of that. So to give you an example of this, right, I'm just going to define a couple of lists for the L2 loss for the training set. So I have a list where I'm going to add my training losses. So that starts empty. And then I'm going to go down here and append the loss, the L2 loss. And I also need to, so that'll be my Y, and I also need some X values, which is the epoch. So I have to keep track of what epoch the L2 loss corresponds to. So I'm going to add the epoch here, and I need to define an empty list up here. So let's just plot that and see how that works. So obviously I have to run it, so my lists get filled. And I'm going to go down here now and plot it. So my X values is the epoch list. My Y values is the L2 loss for the training set. And that should do it. Okay, so we can see we have the losses here. Now there's, in the beginning here, right, there's a very big change in the L2 loss. It goes down very quickly and then less quickly here. So I'm going to lose a lot of, let's say, fine structure here. Yeah, so this region here is not all that interesting, and so I think I just want to plot from maybe 0.025 or something. So I'm going to change my axis. And the X values is fine. I want to plot for the whole range. So I just want to plot from 0 to the maximum value in my epoch list. For the Y values, I still want to start at 0, but now I want to go up to, let's say, 0.025 and see how that looks. So I get an error here. That's because this needs, everything in here needs to be in parentheses. Oops, not in here, but in here. Okay. All right, so that's a pretty good plot. Now let's do the same thing for the validation set. So I need a list. And, oops, and now I need to go down here, and now here I actually have to compute the L2 for the validation set. So that's going to be for my validation. And I need to write a function for that, I think. So I'm going to call that get L2. And then I have to figure out what goes in here. Okay, so I'm going to go up here and make my function. And let's see, so I need, let me go down here. Right, so this is the equation for the L2. And so to do that, I need the error. And to get the error, I need the y and y predicted. So I need to pass in the y. And for the y predicted, I already made a function here called predict. So y predicted, I get from predict. So I need, for that function, I need the weights and I need my xp. So that is the x values with the biases added in, like so. Okay, and so obviously I need to make the xp, I need the x, I have the y, I get the n from the x, I made the xp, and looks like that should work. And then I return the L2 loss. Okay, so this is what I need to call. I should probably run the cell here. And let's go down. Oh, I need that up here. And so here I want to compute this for my validation points. Okay, let's see if that works. It's WIH. So I need to change that here. And I need to change that here. I need to run that again. And let's see. Okay. So I guess the best way to see if this works is just to plot it. So instead of the validation, instead of the training, I now have the validation. That did not work. Okay, my validation list, the length of that is 0 for some reason. Because I forgot to append. Okay. Oh boy. So L2 val list. Oops. L2 val here. And let's see. Excellent. I want to do two things here. One is to label the plots so I know what's what. So that's my training. That's my validation. And then I need to plot the legend, like so. Okay, that's labeled. Now it's a little bumpy, so I think actually here I want to, instead of every 10th, well, not every 10th, so I want 100 points and not 10 points like I have here. Although I don't want to print it out for 100 points. So the printing here I'm just going to do for 10 points. Okay, let's try that and see if I get a nice smooth curve. I do. Excellent. Okay, so the the principle of early stopping is basically just to, and eventually I want to use my model for points that are not in the training set. The training set I already know the y values. So I want to use it for points that are not in the training set, such as the validation set. And so therefore I should really pick the weights, or I should stop the training when the error for my validation set is the smallest. And so that looks like that should be around 5,000 epochs. So basically what I predict now is that if I stop this after 5,000 epochs, I should see a lot less overfitting here. So I go up here and run this for 5,000. Let's see. Yes, right? So you can see that sort of the overfitting here is gone, and also the error for the validation points are no bigger than some of the errors for the training points. So that actually looks pretty good. Let's see how close I got to the minimum here. Yeah, and so 5,000, that is just about the minimum, and so that looks very good. So in general, or avoiding overfitting or reducing overfitting, in general, that's called regularization. And one technique for that I've just showed here is early stopping.